All right, welcome to this explainer. Today, we're embarking on what is basically the ultimate macro to micro detective story. We're going to trace our shared origins from an absolute unimaginable void, all the way to the incredibly vibrant living world we call home today. So if you've ever wondered how the universe literally cooked up everything around us, well, you are definitely in the right place.
Okay, let's dive into this. 13.7 billion. Yeah, that is the sheer scale of the timeline we're looking at today. 13.7 billion years since the Big Bang. It's a number so massive it honestly kind of defies human comprehension, but it's absolutely crucial because it is the ultimate anchor point for literally everything that exists.
And that really brings us to a fundamental question, right? How exactly did a tiny, infinitely hot, infinitely dense point transform into a living, breathing planet? I mean, this isn't just ancient, distant history. This is our history. We're going to follow this chronological narrative arc to see exactly how physics and chemistry perfectly laid the groundwork for biology.
To make sense of billions of years of complex history, we've broken it down into 5 key eras. We'll start with the birth of the universe, move into stars and planets forming, see how the Earth takes shape, look at oceans and air, and finally wrap up with the origin of life.
Starting right at the beginning with Section 1, the birth of the universe, expanding from a tiny ball.
So, before the galaxies, the stars, or even the concept of space as we know it, all the matter forming our universe existed in just one place. It was a singular atom, literally a tiny ball of unimaginable density and infinite temperature. And then, it violently exploded into action. Within just the first 3 minutes of the Big Bang, the very first atom began to form from that rapid expansion. Then, if we jump to 300,000 years post-Big Bang, the temperature dropped to about 4,500 Kelvin. This is a vital milestone because it allowed atomic matter to properly form and the universe finally became transparent. Energy was literally converting into the building blocks of matter right before our eyes.
Now, what's really interesting about this slide is Edwin Hubble's famous balloon analogy from 1920. It's a classic way to picture this rapid expansion. Imagine marking dots on a balloon and inflating it. The dots move apart as the rubber stretches, right? That's kind of how space is expanding between galaxies. But there's a vital scientific caveat here. While the balloon material stretches and the dots themselves might stretch in a real balloon experiment, in our universe, the galaxies themselves are not expanding. The empty space between them is. It's a really crucial distinction to keep in mind.
Moving on to Section 2, stars and planets form, condensing the cosmos.
Let's fast forward a bit to about 5 to 6 billion years ago. The early universe wasn't exactly perfectly smooth. Uneven gravitational forces started drawing matter together into these massive clouds of hydrogen gas called nebulas. Within these enormous nebulas, localized clumps of gas began to collapse under their own immense gravity. And as they collapsed, they grew into incredibly dense, hot, gaseous bodies. Eventually, the pressure and heat got so intense that they ignited, lighting up the cosmos with the very first stars. Gravity was literally acting as the ultimate cosmic sculptor.
Getting from a burning star to a solid planet, well, that happens in 3 distinct stages. First up, a huge rotating disk of gas and dust develops around a star's core. Next, that gas cloud condenses and matter develops into small, rounded objects. Through cohesion, these become what we call planetesimals. You can basically think of them as massive, rocky space boulders. Then, in the violent final stage, these planetesimals aggressively collide, stick together through gravitational attraction, and accrete to form the large, recognizable planets we know today. It was, honestly, a chaotic, cosmic demolition derby that built our solar system.
Which brings us to Section 3. The Earth takes shape, a volatile beginning.
Zooming in specifically on our own planet, roughly 4.6 billion years ago, primordial Earth would be completely unrecognizable to us today. I mean, it was barren, rocky, blisteringly hot, and wrapped in this suffocatingly thin atmosphere of just hydrogen and helium. Contrast that with the present day. We have a beautifully layered planet covered in vast oceans and blanketed by a life-giving atmosphere. The dramatic, awe-inspiring transformation our planet went through is nothing short of miraculous.
Let's move to and see how this builds. As the early Earth existed in this volatile state, especially after a giant moon-forming impact, it literally started to sort itself out.
Extreme heat caused the planetary materials to separate by density. The heavier elements, like iron, sank straight down to the center, while lighter materials floated up toward the surface. This process is exactly what gave us the distinct lithosphere layers: the crust, the mantle, the outer core, and the inner core. Our planet basically organized itself into a layered sphere.
And that sets the stage for Section 4, Oceans and Air, Cooling Down.
So this marks a truly crucial era. After the violent heat of that planetary differentiation, the Earth finally began to cool down, which paved the way for water and breathable air. This atmospheric evolution happened in 3 critical steps. First, powerful solar winds swept in and completely stripped away that thin, primordial shell of hydrogen and helium we talked about. Second, as the Earth cooled, we experienced interior degassing. And third, the living world eventually stepped in. Early life forms used photosynthesis to fundamentally modify the atmospheric composition. They basically replaced early volcanic gases with the modern nitrogen and oxygen-rich air we rely on right now.
Now let's talk about that second step, degassing. This is the process where trapped gases and water vapor were continuously outpoured from Earth's hot interior through massive volcanic eruptions. So the crucial point is that this intense, violent volcanic activity was actually our saving grace. It pumped out the immense volumes of water vapor that eventually condensed, rained down for millions of years, and collected in huge depressions to form our oceans. And those oceans? Yeah, they are as old as 4 billion years.
Finally, Section 5, The Origin of Life, from Chemistry to Biology.
We are now making our most delicate transition, zooming all the way into the microscopic beginnings of life itself. If we trace the milestones, we see that 4.6 billion years ago, the Earth forms. 4 billion years ago, the oceans form as the Earth cools down. Then, roughly 3.8 billion years ago, life begins. But notice the huge gap here. A cooling Earth created a habitable, deep aquatic environment long before oxygen ever flooded the sky. It wasn't until 2.5 to 3 billion years ago that photosynthesis evolved. And it actually took until about 2 billion years ago for oxygen to truly flood the atmosphere. Life survived and thrived deep in the oceans way before the air above was even remotely breathable.
And the absolute proof of this is locked right there in the rocks. Fossils show that microscopic structures closely resembling modern blue algae existed over 3 billion years ago. For a massive chunk of our history, life was strictly confined to the dark depths of the oceans. But, these microscopic powerhouses were busy. Through photosynthesis, they fundamentally altered the planet's chemistry. They slowly saturated the ocean water with oxygen until it literally bubbled up and flooded the atmosphere, setting the stage for complex life on land. It's profound to realize that modern scientists refer to the origin of life simply as a kind of chemical reaction, converting inanimate matter into living substance. When you look at it through that lens, isn't it completely mind-bending to ponder how 13.7 billion years of cosmic, physical, and chemical reactions perfectly culminated to create us, sitting here today trying to understand it all? So what does this all mean for us moving forward? Well, keep wondering about those chemical reactions and keep learning. Thanks for joining me on this journey.